Hello everyone. I haven't yet started the lecture. I'm trying to launch the poll. First question of the poll. So Aryan, don't worry. Am I audible, Aryan? Aryan Bamre, am I audible? Okay, thank you, Aryan. Poll to initiate the discussion. Okay. So I request you to immediately vote so that your attendance. Be waiting for half a minute before I start the discussion. Unfortunately, only 50% of the class has got this answer correct. Whereas the other class is yet struggling to find the right answer. So that is a bit surprising because we had a lot of discussion on this Clausius theorem, both during the online lectures, also in the videos which were shared with you. Pille ma'am, please close the poll. Okay, as you see that the correct answer for this is a reversible cycle. The Clausius theorem we had discussed in the last lecture is applicable only to the reversible cycle. Okay, and what is that theorem that we will be discussing again, and we will be starting with the discussion of today's lecture, that is the temperature entropy diagram. So that is the agenda. Before I start with the question, I want you to tell me whether the whiteboard is visible to you. Yes or no? Okay, it is not seen. Now whether it is visible? Okay, thank you, Himanshu. Thank you, Ankush, Maheshwari. Thank you. So let me begin with the discussion. Please register this that the theorem which we are discussing, okay, namely the Clausius theorem, that theorem is applicable to the reversible cycle. Okay, let me write this. The Clausius theorem is applicable to reversible cycle. Okay, reversible cycle only, and it is not applicable to irreversible cycle. So this you have in mind. And what is this theorem? This theorem is, it states that cyclic integral of del q, cyclic integral of del q by t, cyclic integral of del q by t for a reversible cycle, is equal to 0. This is the theorem. Okay, this you need to remember, right? And this is very useful tool. Let me tell you why it is useful. This is useful because when you are talking about second law, we are talking about the reversibility and irreversibility in terms of qualitative aspect. But if you want to quantify how much is the irreversibility, then this understanding of Clausius theorem will help us quantify. How it will help us quantify, that we'll see later. But just keep in mind that the Clausius theorem, and then what we'll be discussing, namely the Clausius inequality. These are the useful ideas quantify the irreversibility both in the cycles as well as during the processes. How to quantify? Quantify means, I mean to say, get some understanding in terms of numbers. That is plus quantitative understanding. Okay, so that understanding would be improved when we discuss this Clausius theorem and Clausius inequality with reference to the new property which we have discovered. And we have discovered the property by using this theorem, which is called as the property of entropy. Okay, and how did we discuss that? So for discussing this, we can take an example of any reversible cycle. Okay, to prove that there exists a property called as entropy. For example, this is R1, and let us say this is initial state A to final state B. Okay, there is one reversible path which is R1, and if you get back to the initial state by some other reversible path R2, right? Then by application of Clausius theorem, what I had shown you is that this is nothing but del q by t. This is cyclic integral and this is line integral a to b plus via the path R1 and from b to c, b to a back again, del q by t via the path R2, and this according to Clausius theorem is equal to 0. This we had discussed a bit, right? So this is applicable, mind well, this is applicable only to the reversible cycle. This is applicable only to the reversible cycle. We can also consider some other reversible cycle. For example, let me consider this cycle. Okay, just to ensure that you understand it very clearly. that there exists a property which is path independent. I have taken another reversible cycle, for example. Let us say this is your reversible cycle now. So this is R3. So this was the cycle, let us say A, R1, B, R2, A. Okay, this is one cycle, for example. And now let us say that I had considered another reversible cycle for that matter. So let us say this is another cycle, which is the cycle. This is now a cycle. Let us call this as A, R1, B, R3 back to A. Okay. So if you, for example, then again apply the Clausius theorem to this. Okay. So you see that this becomes del Q by T from A to B, from A to B via path R1 plus integral of, again line integral of B to A back again to A, but now via path R3 del Q by T integral is equal to 0. Okay, so this way also, if you compare this now, for example, let me use some other pen. Okay, so now if you compare this equation 1 with equation 2, what you find is that this and this is also the same, right? So it means that B to A via R2 and B to A via R3, okay, integral of del Q by T is the same. So this meaning is this del Q by T integral, this del Q by T integral is path independent. Okay, it does not depend on the path independent, right? And when it is path independent, we had said, what did we say in the last lecture? That this, because it is path independent, this should represent a change in property, and we call it as delta S. Okay, delta S. So in the last lecture, we discovered a property called as entropy. Okay, and we didn't actually define the property of entropy. We defined the change in entropy. Sorry, I had a call. Okay. So we had discovered, we didn't, please note that we didn't define what is absolute entropy. We defined what is a change in entropy. What is a change in entropy? And that becomes as an integral of line integral. Okay, over a reversible path of del Q by T, Okay, and if you consider elemental change, that becomes ds is equal to del Q by T. Okay, as I said, you can also write this as inexact differential this way, dq by T. Okay, so this was what we had proved in the last lecture, Clausius theorem. Okay, so by basing our discussion on the Clausius theorem, which is cyclic integral of del Q by T is equal to 0 for a reversible cycle, we went on to prove that there exists a property called as entropy, whose change is given by ds is equal to del Q by T. Okay, provided the path is reversible path. Okay, so we would be exploring this more, and we would be trying to construct, okay, a very useful property diagram called as temperature entropy diagram in this online lecture today. Okay, so let me use this understanding, that what is the understanding, that ds is equal to del q by t for a reversible path. Okay, this understanding to draw what is called as a temperature entropy diagram in this lecture. Okay, so let me up this all and start anew. Okay, so let me get back to this basic expression of ours. Okay, so what did we say? We said that ds is equal to del q by t, del q by t. Or rewriting, we can say del q is equal to t ds, or or q is equal to the heat transfer q is equal to integral of t ds. Okay. So parameter called as heat transfer, and we are talking about two properties. One is the property of temperature and other is the property of entropy. Okay, so we are trying to relate this temperature and entropy to the heat transfer. Okay, we are in a way trying to relate the temperature and entropy to the heat transfers. Now how is that to be related? Okay, so for understanding this relation, let us consider now that we are drawing a temperature entropy diagram. Okay, you can draw any diagram, but why are we drawing this temperature entropy diagram? This is because we have now discovered a property of entropy, and we are trying to figure out how this property of entropy is useful. Okay, so for that, let me consider some process, any process. I'm not saying a particular process, any process you consider, for example, right? And let us try to out what is ds. What is ds? So would be then ds would be then a very small, infinitesimally small change in entropy. Okay, assume these are vertical lines. Okay, it is difficult to draw a vertical line using this, right, which I am using, right? So this would be ds. This would be ds. So let me draw a hatched line showing this ds, showing this ds. Okay. Now, if this portion which I had drawn as a hatched line is extremely small, okay, this is a infinitesimally small, extremely small, infinitesimally small strip. Means very small. Infinitesimally small means very small strip. Okay, with its thickness, okay, as ds. Okay, and this the breadth is, let us say, ds, and its length is, let us say, it would be some t, some value t. Okay, so this would be, and because this is very small, so we can approximate this, we can neglect this very small change in t, okay, as compared to this total t. So let us say that this is some t. Okay, so what you say is that this t into delta s is nothing but the area of the elemental, the rectangular strip. Area of the length into breadth, you understand, length into breadth is the area, okay, of a rectangle. So t into delta s, this is t, this entire portion is t, this is t, and this is ds. Okay, so t into delta s is the area of the rectangular strip, which is shown by the hatched line. Okay, I have shown this by the hatched area. Okay, so this hatched area, now if you look at this expression, let me call this as some expression, this as expression 1. Okay, let us call this as expression 1. Okay, so if you reflect on equation 1, and if you reflect on this, then what it means is that this hatched area is giving us the elemental heat transfer. It is giving us this elemental process. So if this is 1 and this is 2, and let us say that a part of this process which is A and B, where A and B are close enough, okay, they are almost coinciding. A and B are almost coinciding, okay, almost coinciding. It means that it is an infinitely small difference, okay. So then Ta is equal to Tb. T is what? T is, in this case, Ta is equal to Tb, okay, into delta S, which is T into delta S. This is the area of the rectangular strip, which is nothing but the elemental heat transfer del Q. Elemental heat transfer del Q. So if you integrate it, if you integrate this expression between 1 and 2, if you integrate this expression between 1 and 2, so what is the meaning of integration? The meaning of integration means we are now interested in this area under 1 to 2. Okay, integration means what? We are now interested in this entire area which is under 1 to 2. Okay, so the entire area under 1 to 2, which is nothing but the integral of from one line integral from 1 to 2, TdS is nothing but the total heat transfer during the process. Okay, it is the heat transfer during the process, during the process 1 to 2, and that is the beauty of the property of entropy. Okay, what it tells you is that if you are able to plot any process on a temperature entropy diagram, if we are able to plot a process on a temperature entropy diagram, then the area under that process would be the heat transfer associated during that process. Okay, it is the heat transfer associated during that process. Is this clear? So this you need to keep in mind, that because of the heat transfer there is a change in entropy. This we had discussed. Look at this expression. When you are talking about ds is equal to del q by t, and I had considered this elemental process A to B. Okay, so it gives you the heat transfer during A to B upon T. So why has this entropy changed? This entropy has changed because of the heat transfer. So the entropy change, okay, and this is a reversible process we are talking about. Okay, we are not talking about irreversible process right now. So let's note that we are talking about a reversible process. Then this entropy change is because of the heat transfer. Okay, heat transfer. In a way we can say that because of heat transfer there is an entropy transfer. Okay, and that entropy transfer is now obtained, that entropy change is now obtained by the area under the curve. Okay, so this is the significance of the property of entropy, and hence it is useful for us to plot a temperature entropy diagram. So why should we, what is the significance of temperature entropy diagram? The significance of temperature entropy diagram is that it gives us a easy way of determination or exploring the heat transfer during the process. Okay, that is the beauty of the temperature entropy diagram. Okay, so now we have done, let's summarize what we have done. First thing is that, again, at revise that using Clausius theorem, which is applicable to a reversible cycle. Okay, a reversible cycle, cyclic integral of del q by t equal to 0. Using this, we had shown the existence of property called as entropy. Is given by ds, said that is use of this fact, okay, temperature entropy plot. So if we had considered a process, some process 1 to 2, then using this expression ds is equal to del q by t, we went on to show that for any elemental area, such that, sorry, okay, for any elemental area, let me just redraw this. For any elemental area, we had shown that this elemental area, which is the area under this process line, would give us the elemental heat transfer, which is P into delta S. Okay, and then we said that the total heat transfer, which is the area under this curve, can be obtained as an integration of TdS, which is the area under the process line, on. So heat transfer is nothing but area under the process line on temperature and diagram. Okay, temperature entropy diagram. So using this understanding, now we are going to discuss two very special processes. And when I'm saying there are special processes, they are special because they are the part of the Carnot cycle. Okay, so reversible process. Okay, reversible adiabatic process. What is the change in entropy during this process? Okay, if it is elemental ds or if it is a total process delta S, how much is that? Okay, so for finding this, we must know what is an adiabatic process, and we must know the expression for entropy. So I am taking okay for a reversible process. Now you see that we are talking about a special process, namely an adiabatic process. We are talking about a reversible process, but we are talking not of any other process. We are talking about a reversible adiabatic process. Now, what is the meaning of adiabatic process? The meaning of adiabatic process is that the heat transfer is so making use of this fact, that is in equation 1 and equation 2, we can say that from 1 and 2, why is del q is equal to 0? Because the process is adiabatic. Okay, and the process is reversible. Okay, so del q is equal to 0 because the process is adiabatic. And why we can apply this equation? Because it is a reversible process. Okay, so then using 1 and 2, from 1 and 2, you know that you just mathematics now, ds is equal to 0, that is change in entropy is 0, or entropy is equal to constant. So when the process is reversible adiabatic, then you see here, that process happens to be a constant entropy process. And constant entropy process is known as isentropy or isentropic process. Okay, this is an important finding, that a special process, namely a reversible process, which is an adiabatic process, a reversible adiabatic process, in that process the entropy does not change, the entropy remains constant. That process is a constant entropy process or isentropic process. Okay, so if I want to represent this process on a temperature entropy diagram, okay, so let me represent this process on a temperature entropy diagram. Now, which process I am representing? I am representing a reversible adiabatic process on a temperature entropy diagram. Okay, so look at this process, a reversible process. A reversible process on a temperature entropy diagram would be a vertical line. Why it would be a vertical line? Because suppose you are considering a process 1 to 2. In that case, so if it is a reversible adiabatic process 1 to 2, 1 to 2, then it follows that entropy at 1 is equal to entropy at 2, because we had shown that if it is a reversible adiabatic process, the entropy does not change. So if it is a constant entropy process, obviously on a temperature entropy plot, this S1 will be equal to S2, and this process has to be shown a vertical line. Okay, whether the temperature would increase or decrease would depend upon whether the process is of expansion or compression. So it means that in the Carnot cycle, we had said that there are reversible adiabatic processes. Okay, so both these two reversible adiabatic processes in the Carnot cycle, they are isentropic processes. Okay, this you should be very clear, right? So on a Carnot cycle, if I want to represent the Carnot cycle on a entropy diagram, then the two processes which we talk about in the Carnot cycle, they are vertical. Okay, this is the beauty of the temperature entropy diagram. Now let us talk about other process which is an important process in the Carnot cycle, and again a special process which is a reversible isothermal process. Okay, so let me rub this first. I have stated this very clearly that if the process is reversible adiabatic, then the entropy remains constant. What if the process is reversible isotherm? What if the process is reversible isotherm? So let me rub this. What if the process is reversible isotherm? What would be the entropy change if the process is reversible isotherm? Okay. So if the process is reversible isothermal, and to be very clear on this, that though it is a temperature is constant, does not mean that entropy is constant. And this, let me show you by using our basic expression. So your ds is del q by t. Okay, or delta s during the process, let us say 1 to 2, would be what? It would be integral 1 to 2, integral from 1 to 2 of del q by t. Okay, I am talking about now. So this is for any process. Okay, any reversible process. But if it is a reversible isothermal process, then if it is a reversible isothermal process, so let me write down this reversible isothermal process, then the temperature is constant. So temperature is constant, and you have studied in mathematics that if your temperature is constant, in calculus you have studied that this temperature can be taken outside the integral. Okay, so it means that delta s 1 upon t integral of del q, and integral of del q nothing but the heat transfer during that process upon t. Okay, is this clear? Please note that though we are talking about a isothermal process does not mean that the entropy is constant. Okay, the temperature is constant, entropy does not change. So entropy does change. Okay, entropy does change. Now what will happen, whether the entropy will increase or decrease? So as I had given you when we are talking about the conceptual understanding of entropy, I had told you that whenever there is a heat transfer to the system, okay, heat transfer would be the entropy, because along with the heat flows the entropy. This you have to remember it very clearly, that along with the heat flows the entropy. When you are transferring the heat, sorry, this spelling is entropy, not ry here. So when you are transferring the heat to the system, the entropy will change and it will increase. Okay, so even if it is a reversible heat transfer, the entropy would change. So for example, if I want to plot the reversible isothermal process of heat addition, isothermal means temperature would be constant, so it will be a horizontal line. Because it is a isothermal. Okay, but the entropy would increase if there is a heat transfer. It would increase from S1 to S2. That is S2 would be greater than S1 if there is a heat, or the entropy would decrease, from, if this is 1, let us say this is 2, and I'm calling this is process 3 and this is 4, the entropy would decrease if there is a heat rejection. The entropy would decrease if there is a heat rejection. So if there is a reversible isothermal heat transfer which happens in the Carnot engine, then the entropy increases. So in the Carnot cycle, when there is a reversible isothermal heat transfer, the entropy would increase from S1 to S2. When there is a rejection of heat, which is again an isothermal heat rejection, then there is a change in entropy from S3 to S4, and you see that the entropy decreases. Okay, so entropy would increase if there is a heat transfer to the system. Entropy would decrease if there is a heat rejection from the system. Okay, so if I want to plot, so this need to be very clear that one thing you need to be keeping in mind is that when the process is reversible isothermal, the temperature remains constant, the entropy does not remain constant. Okay, so now I had shown you that if the process is, I had discussed this, that when the process is a reversible adiabatic process, the entropy remains constant. If the process is, let me once again write down this very clearly, if the process is reversible adiabatic, then on a temperature entropy diagram it is a vertical line. If it is a reversible isotherm, then it is a horizontal line. Okay, I am talking about temperature entropy diagram. Okay, so this is a isentropic process. Why it is an isentropic process? Because the entropy is constant. Okay, and it is a vertical line. The direction would depend upon whether it is an expansion or compression. And this is a isothermal reversible process. Both are reversible, I am drawing. This is an isothermal process. Here what happens to the entropy? Entropy would change, but what would remain constant? So temperature would remain constant. Okay, so this you have to be very clear that when you are talking about a reversible adiabatic process, the entropy remains constant, so it is isentropic and as a vertical line. If it is an isothermal process, the temperature remains constant, it's a horizontal line. Okay. With this understanding, now let us draw the Carnot cycle on a temperature entropy. Okay, we had already plotted the Carnot cycle on a pressure volume diagram. So let me plot the Carnot cycle on a temperature entropy diagram. Okay, so let me write down the processes of Carnot cycle first. Carnot cycle on temperature entropy diagram. Okay, so let me first write down the processes. 1 to 2 is reversible adiabatic process. 2 to 3 reversible adiabatic heat transfer process. I will start with isothermal first. Okay, it doesn't matter. So anything you can start with. A reversible isotherm heat transfer process, which is associated with expansion. 2 to 3 is reversible adiabatic expansion. 3 to 4, I will call it as, you can call it as ABCD 1 2 3 4 5 6 7 8. That is not important. Okay, concepts are important. So reversible isothermal, I am writing it in short, isothermal heat rejection. Now there is a heat transfer, means heat supplied I am talking about. Here it is heat supplied. Both are heat transfer, but one is heat supplied, other is heat rejection. And 4 to 1 is reversible adiabatic compression. Okay, now what I am trying to do is that, based on our discussion which we had now, I am going to plot it on a temperature entropy diagram. Okay, temperature entropy diagram. So isothermal means now T1 is equal to T2 is equal to TH. Okay, higher temperature. So let us say that this is your TH on the higher side. So then this would be 1 and this would be 2. Okay, and because there is a heat supplied, heat is being supplied, so the entropy would increase from S1 to S2. Entropy would increase from S1 to S2. Now 2 to 3, 2 to 3 is reversible adiabatic, and I had shown you that this will lead to constant entropy. Entropy would remain constant, right? Constant, and because it is expansion, so the temperature will drop. Because it is an expansion, the temperature will drop from TH to TL. Temperature will drop from TH to TL. So let us say this is TL. Let us say this is TL. So this will be a vertical line. This will be a vertical line. Vertical because the entropy at 2 and 3 is same. Entropy at 2 and 3 is the same, right? Now, if you consider the next process, which is again an isothermal process now. So T3 is equal to T4, which is equal to lower temperature TL. Then this would be a horizontal line again, and because now the heat is being rejected, okay, so this would lead to the decrease in entropy. This would lead to the decrease in entropy. So the entropy would decrease from S3 to S4. Entropy is now going to decrease, right? And now the next final process is a reversible adiabatic compression. Because it is reversible adiabatic, the entropy remains constant. So S4 is equal to S1. So because it is S4 is equal to S1, and because it is compression, the temperature will increase from TL to TH because it is a compression, and because it is a reversible adiabatic, the entropy remains constant. So it will be a vertical line. Okay, so it becomes a rectangle. So area under 1 to 2 would be heat supplied, area under 3 to 4 would be heat rejected, and this hatched area is the net heat transfer. Okay, that is the net heat transfer, because I told you that significance of temperature entropy diagram is the heat transfer. So it will give you the heat supplied minus heat rejected. What would be the heat supplied? The heat supplied would be the heat supplied during the process 1 to 2, and it would be equal to the area under 1 to 2. And what would be the heat rejected? The heat rejected would be the heat rejected, let me write it over here. Heat rejected would be the heat rejected during the process 3 to 4, okay, which is equal to the area under 3 to 4, right? And the difference in the area, which is the hatched area, is the net heat transfer, which is heat supplied minus heat rejected. What is the heat supplied during the process 2 to 3? You see there is a vertical line, so the area is 0, so the heat supplied is 0. What is the heat supplied or heat rejected during the process 4 to 1? It is a vertical line, so the area under this curve is 0. So the heat supplied or heat rejected during this process is 0. It means that the processes 2, 3 and 4, 1, they are adiabatic processes. Okay. So this is the concept of, or this is rather the usefulness. Okay. This is rather the relevance of defining the term of entropy and plotting the temperature entropy diagram. So we had discovered the property of entropy, and now we are starting to use, okay, we are now starting to use this property of entropy for gaining more understanding of physical systems. Okay, so for that we have now discussed how this property of entropy is useful to understand the Carnot engine. Carnot engine, obviously it is a reversible engine, it is an ideal engine. Okay, but even if the engine is irreversible, this property of entropy is going to add insights to our understanding and help us appreciate and help us improve the efficiency of the actual engines. How that would happen, that discussion is later. Okay, but for the present purpose, try to understand that how this temperature entropy diagram is drawn, how it has come, okay, how the property of entropy change was defined, that is ds is equal to dq by t, from the logical extension of second law of thermodynamics and application of Clausius theorem. Okay, hopefully you understood this. Let me check whether you understood this by giving you the poll questions. You need to be very quick in answering it. Okay. Just a minute before we launch these questions. There is some technical issue from our side. Okay. So the answer to this question is entropy is a property. The answer to the question is entropy is a property. It is not a path function. It cannot be obviously path function and property together. It has to be a property. Okay, so entropy is a property. That is the correct answer. The next question is about the area enclosed by thermodynamic cycle on a pressure volume diagram. So diagram uh, is basically giving you the work transfer, and the temperature entropy diagram would give you the heat transfer. Okay, this you need to be very clear now, that what is the significance of pressure volume diagram. The pressure diagram will help us calculate the area enclosed, for example, in a thermodynamic cycle, whether it is a Carnot cycle or some other cycle. The area enclosed in pressure volume diagram, that area, closed area, would talk about the net work transfer, okay, during that cycle. And similar to that, as we were discussing now, that when we are talking about a temperature entropy plot, then that area which is enclosed in the temperature plot would give us the heat transfer. Okay, this you have to be very clear, that area enclosed by the temperature entropy plot would give us the heat transfer, the net heat transfer, I say. Okay, in this example which I had taken, in the Carnot cycle, we had seen that 1 to 2, area under 1 to 2 would be the heat supplied, and area under 3 to 4 would be the heat rejected. Okay, heat rejected. And I told you that when the process is reversible adiabatic, then the entropy would not change. Okay, the entropy would remain constant. And because the entropy remains constant, the process is called as an isentropic process. Okay, the process is called as an isentropic process. So in an isentropic process, the entropy remains constant. That you need to be very clear, right? And we had already discussed that if the process is isothermal, okay, and if there is a heat transfer, then the entropy would change, though the temperature does not change. That has to be very clear. So all these questions are framed so that you revise the concepts. You are very clear on the concepts. Uh, First question was about Clausius theorem, where it is applicable to. Obviously, it is applicable to a reversible cycle. Then what we said, what is entropy, whether it is a state function or point function. So entropy is a point function. It is a property. Okay, it is not a state function. Sorry, it is not a path function. Entropy does not depend upon the path. It depend because it is path independent. Hence, it is a property, and we had called it as a property of entropy. Okay. Um, though I didn't discuss that what is the significance of pressure volume diagram, but in the video which was shared to you, it was shown by Professor Murukar that the significance of pressure volume diagram is that it gives us the work transfer. Okay, so when you are talking about a pressure volume diagram, and if it is a closed system, then the area under that process would give you the work transfer. When you are talking about a reversible adiabatic process, I told you that because the process is adiabatic, because it is a reversible, then the entropy remains constant. The entropy does not change, and this we had shown by using the simple expression ds is equal to dq by t, where dq is equal to 0, and hence your ds is equal to 0. That is, s is equal to constant, right? So a reversible adiabatic process is an adiabatic. It is a constant entropy process. It is also called as isentropic process. Iso for constant, entropy process. Constant entropy, so isoentropy, hence isentropy, right? And I'd emphasize that when it is an isothermal process, though it is a reversible isothermal process, and whenever there is a heat transfer happening, then that heat transfer would change the entropy, because along with the heat flows the entropy. Okay, if there is a heat addition, then that would increase the entropy. If there is a heat rejection, that would decrease the entropy. Okay, and then we talked about the temperature entropy diagram, and I had plotted the Carnot cycle on a temperature entropy diagram. I had shown you that if you are talking about the area under a temperature entropy diagram, and the area under the temperature entropy diagram would give us, it will talk about the heat transfer. It does not talk about the work transfer. Okay, whereas the area under the pressure volume diagram, if it is a closed system, it would talk about the work transfer, right? And if we are talking about the enclosed area, then it is nothing but the net heat transfer during the process, right? This I had explained you by giving an example of Carnot cycle. I had plotted the Carnot cycle on the temperature entropy diagram, and hopefully all these concepts are clear. Okay, so if you are clear on all these concepts, please say yes. If you are not, please say no in your questions column. If you are clear on this, please say yes. If you are not clear, please say no. This, all of you? Yes or no? Whatever we are discussing. Put your responses in the questions column. If you are understanding it, please say yes. Okay, thanks all of you for joining this lecture. If you are unable to get the concepts right, again our advice is that you need to revisit the videos which are being given to you. Okay, there are texts also you can refer to, and if you have any specific query, you can ask those questions during the lectures. Okay, so thank you very much for joining. Have a good day.